Hello, ladies and gentlemen, and welcome to today's web seminar with the topic Gear Excitations in the FVA Workbench. My name is Tazir, and I'm working for the FVA GmbH as software developer. And before, I worked around 10 years for the automobile industry as gear designer and analyst for manual transmissions. I planned for today's web seminar to show you the following steps. First, I'd like to introduce to this topic gear excitations with the basics and our scope for this presentation. Then we'll show you the toolbox, which is available to reduce the gear excitations and micro modifications. After this basics, I will start to show you live the FVA Workbench and how to do a first gear mesh improvement. The second short topic will be scripting, because in my opinion, this is a very absolutely necessary for daily work to make your work easier and faster. And last but not least, I will show you the eigenfrequencies and eigenvalue analysis, which is important to avoid resonances in the system. At the end, I will do a short summary, and I hope there will be enough time to answer your questions. Otherwise, I will do this later on per mail. What is the FVA Workbench? It is a comprehensive tool to design and analyze gearboxes, and it contains a variety of components such as shafts, cylindrical gears, bevel gears, bearings, housings, and so on. If you'd like to know more details, you will find a description of the modules on our website under Software Features. And also on this website in the section Software Tutorials, you will find recordings of past web seminars. Today we are talking about gear excitations. They occur because of periodical changes of the gear mesh stiffness, caused by geometrical tooth form deviations and elastic deflections under load. These excitations lead to vibrations in the system and spread through shafts, bearings, and the housing. This is often called the noise path. At the end, these vibrations may lead to noises, means audible airborne sound. For periodical gear excitations, it is called gear whine. Noise is one of the three big targets of the gear design process. The other both are the load capacity and the efficiency. And the challenge is now to find the best possible compromise for this conflict of aims. But today we are only talking about the excitations and the reason for that. They are caused by the stiffness of the whole system, means all the components like shafts, bearings, housings, and so on, all parts which have an effect on the gear mesh misalignments. The biggest effect on the stiffness changes has the gear design itself, means the macro and micro geometry, especially with the number of teeth, the contact ratios, and the manufacturing deviations. Our scope for today are the modifications and the excitations. The periodical changes of the mesh stiffness is caused by the change of the single tooth pair stiffness, and this is similar to the length of the actual contact lines. But it's not identical because it is difference in the contact line. Is it on top of the gear or on the bottom? Then the stiffness is a little bit different. Here at the spare gears, you can see mostly one or two tooth pairs in contact. Each contact line starts and ends with full length, and this is leading to a significant jump in the stiffness. Here you can see the double mesh area with two contact lines, and then the single mesh area where the stiffness drops down. To reduce the stiffness fluctuations, we can reduce the stiffness in the double mesh area with some micro modifications, but this I will show later on in detail. But you can see on this picture that the basic macro gear design is very important for the performance, because we can only reduce the contact stiffness and we cannot add stiffness. At the helical gears, it is significantly better for lower excitations, because here we have usually two or more tooth pairs in contact. The mesh starts and ends with short contact lines, so the stiffness changes are much more smoother than at spare gears. To evaluate the gear excitations, typically the change of the transmission error is used. And what is the transmission error? It is the difference of the rotational movement between pinion and gear. It can be used to compare the gear stages with the same geometry, but different deviations and modifications. Another criteria is the excitation force. It is the difference of the tooth force between pinion and gear. And a more detailed factor is the tooth force level. It is calculated with the excitation force, weighted and summarized, so it takes the audibility of the human ear into account and has decibel as unit. In the following examples, we will always look at the transmission error fluctuation, but I think this is enough for the excitation. Now we come to the toolbox, which we can use to reduce the gear excitations, the micro modifications. For this, we have to understand the interactions of the meshing direction and the micro modification direction. You can see here at the spur gears, the meshing direction means the contact lines are moving in profile direction. So each modification of the profile takes effect on the transmission error. All modifications on the lead direction means over the phase width don't affecting the transmission error. For helical gears, it is different. Here the helix angle is leading to a diagonal meshing direction over the contact phase. And so all modifications in profile and lead direction have more or less an effect on the transmission error. If the helix angle is large, the lead modifications are more important. If the helix angle is very small, we get more or less the same relationship like at spur gears. Which micro modification exists and are usable in the FVA Workbench? Starting with the profile modifications. We have the profile angle modification, which is compensating the center distance deviations, and it is leading to a deviation from the ideal involute. The pictures of the mesh topology and the inspection chart are standard outputs of our reporting. Next, we have the profile crowning. This is similar like a small and smooth tip and root relief. And then we have the tip or root relief itself. Here we can specify the mount and the beginning of the relief, but also the form, like linear, circular, or logarithmic. With these profile modifications, the stiffness and the path of contact can be influenced precisely, especially for spur gears. In lead direction, we have the helix angle modification, which is important to get a centered contact. We have also a crowning in the lead direction, which is important to relieve the edges and to avoid hard edge contacts. And then we have the end reliefs, which are similar to the tip and root relief of the profile in the profile direction. Here we can specify again the form of the relief. Additional modifications are those which affecting the profile and lead direction. Here we have the triangular tip and root relief. This is a very effective modification for helical gears to reduce the stiffness of the double mesh area and to reduce the gear excitations. This is similar to a tip and a root relief at spur gears. Next, we have the twist. It was in the past more a manufacturing error caused by the grinding process. But if the direction of the twist is like shown here in the picture, then we have a relief at the begin and the end of the meshing, means a similar effect, but a lower effect like at the triangular relief. The last modification is the matrix modification. Here you can specify everything you need, like a topographic modification by measurements and so on. If you'd like to know more about micro modification design with respect on load capacity, efficiency and dynamic and so on, then you can find on our website in the section training some live online seminars by Professor Dr. Inge Bier of the Ulm University of Applied Sciences. Now we stop the theoretical part and start with the first and main live demonstration of the FVA Workbench. Let me switch. You can see now here, this is our graphical user interface. I will start with here this housing here. And here are our examples. And I choose the single stage industrial gear unit. Load the model. We wait some seconds until it's loading. We can see now here is a 3D built 3D view of the transmission. You can see the housing is closed. It's an FE housing. Let me cut it off. Therefore, I will do the cut, and I switch to local cutting plane. And then you can see there's a transmission housing, 2 shafts, 1 single cylindrical gear stage. The shafts have bearings, and the load input and output. The first thing I typically do at this beginning is I select here the gear unit, and then I deactivate all calculation targets. Today we like to analyze the load distribution, gear force excitation. The power flow is now here, it's untouched. It's only 1 load up to close to 6,000 Newton meter load. At the moment we have here, you can see here the cylindrical stage in the model tree in the upper right by left corner. And you can see here we have our gear number 6 and gear number 8, and there are no modifications specified. So we will do a first run without any modifications. Therefore, we can do here the calculation. For excitations, I always run system calculations because we need the system deflections. Otherwise, it's not so meaningful. That doesn't make sense. Because if I will select the component and will do a single component calculation, then there's no gear mesh misalignments, no deflections of the system included. So I will run the system calculation. And now we got here a snapshot of our model. Means there are, in this file, there are the input data and also the results of our analysis available. I will rename this in unmodified. I can store this also, save this in the model itself. Otherwise, it is temporary here. This is up on you if you like to do this. We can select a report template. I like to see the results now, and therefore I have to specify which kind of output should I get presented. I can see here you can choose a system report. It's predefined. It's more or less an overview of all capable outputs. We have an overview report. Here's a compact report for key excitations. But for us now, for our webinar, I have customized it a little bit to make it easier to see what I like to show. And so I have done a key excitation user-defined report. If you like to specify your report by yourself, you can do here a customer report. You can see just a short sneak on customizing reports. You can see I choose here some pictures and diagrams. We have templates, table templates, and diagram templates, and can add here and specify what I like to see in the report. Let me open the report. You can see here now it's a standard report. You can see the load distribution. You can see that this is a tilting in the gear mesh. The line load is not even. You have a modification proposal, therefore. So the tool is telling me if I have an helix angle modification of 40 microns, the contact will be centered. Keep this in mind. I will use this value later, the next step. What we have more in this report, we have here the load distribution. This is 3D contact analysis. You can see the contact is at the edge here, a big tilting in the contact. You can see here the tip and the bottom of your contacts are stress peaks. This would be here the 3D modification proposal. Also very nice, but it's not a parameter recommendation, so it's a topographic proposal. Here you can see the mesh topology. That's all modifications, the summary of all modifications. You can see it's plain, so I have specified nothing for the first run. Later we need this as a recommendation for the tip relief according to SIG. Then we have the basic of all excitations is the mesh stiffness fluctuation. You can see here the average flank form. This is again the micro modifications in the contact. And then as a result, you can see here the 3D transmission error over the rolling path. And what is interesting for us is not the absolute value of the transmission error, but for us it's interesting the fluctuation range. We're starting here with 6.23 microns. This is for the peak-to-peak transmission error from maximum to minimum. And this is the excitation we want to reduce. If you're doing a fast Fourier transformation on this transmission error, you will get here this spectrum of the amplitudes for the different orders. Now we have here 2 matching orders, but you can also refine this, can specify in the workbench 3 or 4 or more matching orders depending on your needs. Then another outputs are here the force excitation. You can see also here fluctuation in the contact forces, and also here the force excitation levels spectrum. But now we will go back to the workbench. Now we'll start with modifications. And therefore, I choose here the gear. You can see it's highlighted here in yellow. The gear number 6. We'll add a component and modification. Here I have the choice if I want to read in the measurement data from the GDE file, or if I want to specify the left or the right flank. Standard is both flanks equal specified, and this I will use for today. Now I have a new component. It's called modification 242. And you can see here in the editor what is possible to define. You have a general information here. This is how the specification range is defined, the definition range over the path of contact, and if you the profile and the lead the phase direction. Here you can specify if you were no more details. The standard here is specified for the entire mesh. It's default, we let it so. Then we have here on the position for phase or lead modifications. Here are the helix angle modifications, the lead crowning, the left end relief, the right end relief, and the left and right end relief. For the profile modifications, we can specify the profile crowning, the tip relief, the root relief, and the profile angle modification. The additional forms modifications are the generated triangular tip relief and the triangular root relief, and the offset is a little bit bad wording where we change it to twist. This is our twist. And last but not least, we have our modification matrix. You can read in via a file or type in directly like you want to do. For us, our first step, there was a recommendation to do an helix angle of 40 microns. Therefore, we have to check this here. Here you can specify the directions according to 40E, according to DIN, or according to the modeling direction. We let it according to DIN and say 40 microns. Run again our calculation. Take a look on the results. And now you can see it's not centered. It's still a tilting. And there's still a recommendation of adding around about 13 microns. Why it's not 0? Because we added here a helix angle in our mesh, and then we get with rerun a new system behavior, a new gear mesh misalignments, another system deflections. So it's an iterative process. You cannot do it with one step. Now here you can see that the system is changed, and I should add here 13 microns more in the helix angle. So we go back. We'll type in 53 microns. Run again. And again, it's not completely centered. There's something missing here. Not so bad, but not finally centered. We'll go back, and now I know it's a nice even number, 60 microns. Sorry. And now we can see now the contact is centered. You can see there's no recommendation of helix angle modification, but you can see there's a higher load and the phase begin and the end of the phase width. To make here a straight line, with the recommendation say we need a grounding, a lead grounding of 3 microns. But we want to have at the end a significant larger grounding to get a relief on the begin and the end of the phase width. So we will add a lead grounding of 10. Therefore, we have here lead grounding taken in consideration. We can choose here symmetrical or asymmetrical or whatever, parabolic, but we let it symmetrical and say 10 microns. Run the calculation again. Take a look on the report. You can see we have a nice phase load distribution with reliefs at the begin and the end. But then we take a look on the load distribution and we can see there are high stress peaks, or in this case load peaks, at the top and the bottom of your contact. So we need a tip relief, tip and a root relief. For your opinion, but I don't like root relief, so I will cover this with a tip relief on the pinion and the tip relief on the gear. Therefore, we go to the profile modifications. We have a tip relief. I activate this modification. Here can choose linear, the form of the tip relief. Linear is a little bit hard. You have between your face and your tip relief, there's a hard edge. I like a little bit smoother. I will choose a circular one. Then, short look back. There was a recommendation for the tip relief. Here it's a recommendation for the tip relief according to SIG from the ACMA paper, and you can see the recommendations should be a tip relief of 25 up to 30 microns. 30 is a little bit much. I will do 25 microns. So I choose 25 microns tip relief for the pinion. The length is here I can specify the length of when it should begin. Otherwise, I can specify a short tip relief. Short tip relief means this is starting. The beginning of the tip relief is in the middle of the double mesh area, and the long tip relief is at the beginning of the double mesh area. And I think this is the best choice because we want to decrease the stiffness of the double mesh area. Now we have the tip relief on the pinion. Then we need a tip relief also on the gear. We add here a component, a modification, both flanks. Then we have here our new component modification, subcomponent of cylindrical gear 8. We have here the profile modifications. We have tip relief. We say again it's a circular tip relief of 25 microns. In the beginning it should be a long tip relief. And then we run again. And now this is unchanged because we only changed the profile. And here we can see we have release on top and bottom, and the load is decreased. You have no stress peak, no more stress peaks. Now I want to see what does it mean for our transmission error. Therefore, I like to do a comparison of our designs. We have our unmodified designs. This I would set as a reference. And the last modified design I will set compare with reference. Then I would go get both results side by side. Here on the right side it's unmodified. On the left side it's a hopefully finished modification. You can see load distribution that was the beginning with high peaks and uncentered. This is well done here. And for the transmission error, you can see the mesh stiffness fluctuations is significantly lower. We have no modification specified. You can see here this is a free transmission error without modifications for this design point of 6.23 microns. And with the modifications, we get only 0.98 microns fluctuation at the transmission error. So now we have done our first microgeometry design for one design point. But depending on your needs and on your application, you need more torque levels. This is now only one design point, means one torque level. Then therefore we have to add more torque levels in our model. Can switch to this model back. Then we need load spectra. We have here our local data pool. Then I will add here a value, data from our global database. Another screen. Second, here you can see here I will choose a load spectra, and I like to have 10 load stages. Now I have here in the local data pool of our model, directly in this file, I have here the load spectra. And this is here 10 levels. So this first level is factor 1, means 100% torque. And then it's going with 10% steps down. Here it's only 10% of your max torque available. Then we have to define this in our model. Therefore, we go back to our gear unit with calculation targets and say consider load spectrum. I will number of operating points, it's 10 spectrum, so I will specify 10. You can see now gear force excitation. There was an add-on here in load spectrum. But we want to have now here the calculation for load spectrum. We have not defined our power flow. So we go to power flow, say here for the gear we want to analyze. The load spectrum is here 10 stages. Time share is 1 because you have only one load spectrum, so don't care which the time share is. Okay, then we can see here 6,000 and 10% steps down. We run the calculation, and then this will take a couple of seconds. Now we run 10 load cases with our design. Take a report. I know that the result at the bottom. You can see here the transmission error across the load. This is the maximum transmission error here of around about 6,000 Newton meters, and then 10% steps down to 10% load. Here you have all the transmission errors over your torque. And the same for the orders, if you want to analyze here the special orders of your amplitudes. Okay, and with this kind of view, you have the chance to find a good trade-off for your micro modification design, depending on your load cases. If you have a huge torque range, you should consider to get a good compromise for your modification. It could not be maybe the best for the design point, maybe the best for the complete sweep. Then we go back to our presentation. This was our live demo example 1. And now I will give you a short sneak on scripting. Because for me, it's very important for more efficient and easier daily work with FVA-Workbench. Especially for the micro modifications, we often need the analysis of the possible tolerance range caused by the manufacturing deviations. Also, some optimization over the torque is possible by scripting, and we can run a lot of variations and load cases to find the best compromise for conflict of aims. Last but not least, we can interact with Excel for input and output to get the data directly in Excel for later post-processing. I think the most people are using Excel for post-processing, so it's nice if you get it directly in Excel. Here we can see a the tolerance analysis of the micro-modifications by WZL Aachen. This is a nice post-processing in form of stamp plots to find the tolerance range with low transmission errors. Next, we can see a tolerance analysis over torque with a possible post-processing for frequency distribution, the accumulated probability, and to get with which probability and transmission error occur. The last example is the final drive of a manual 6-speed transmission. Here the gear mesh is getting completely different conditions for the gear mesh misalignments depending on the driven gear. Means if you're driving first gear or 6th gear or reverse gear, if you have drive or coast load case. This is an example where a scripted multiple simulation run can cover all possible conditions of your final drive gear mesh, and then you can find a good compromise for the micro modifications. If you want to know more about scripting and reporting, then you can participate in our next web seminar beginning of May. In this short scripting example, I will show the Excel interactions of our FVA-Workbench 7 development version. I think the Excel interactions and functionalities are extended, but this kind of analysis can be also done with text files in the actual FVA-Workbench version 6.1. Let me switch to our version number 7. You can see here I've prepared for scripting. I have prepared one model. You can see here it's this very simple single cylindrical gear stage. I have prepared this for a run. Means I have specified load distribution calculations for the gear force excitations. I have added micro modifications on the pinion and on the gear. And now I can run this for one single style, but I will show here the scripting. Therefore, we need an additional view of the scripting. You can see here a scripting overview, scripting sheet. Scripts you can save inside of your model. You can load it in your model, or you can save it as external scripts. And think is a very nice thing. You can start your scripts directly in your tool, or you can save it via a batch file. Then the graphical user interface is not open, only the calculation modules are open. Let me shortly describe what I like to do with this script. I like to show you, this is an Excel file, this is our input file. I'm telling the tool, the script, I want to change the stage ID 3. I want to have design A and design B and compare this together. Means I will do a run with A, here I will specify the modifications of the crowning, the profile angle, the lead crowning and the helix angle modification. My first design will unmodified 0, and the second design I choose a little bit crowning, profile, and lead direction. At the end, the script should write the results on the result writer here in Excel. And so just a short view how it's built up. We specify the model path, where it is, how it's the name of the input file, how it's the name of the output file. Then we check if the output file is open and write protected. And then we are starting with reading the stage ID. And with the stage ID, we can get the subcomponent IDs of the gears and the modifications. And then we read from Excel the workbook data as input into these variables, profile crowning, profile slope, lead crowning, lead slope. And these parameters here, we will set the attributes in our workbench model to these parameters. Then we run the system calculation, and at the end we open the result writer, the result sheet in Excel, and write there the results of the torque, spectrum of the pinion and gear, and the transmission error. The same for the design B, and at the end we write the file. I will run this file, and now you can see It's more or less the same like before. This is 10 loads levels I have specified. This is one run with design A and one run with design B. And after each run, you will get the results as snapshot here in your report manager. Nope, this will take a couple of seconds more than the other calculations. So this is the first design A. And typically the second design is a little bit faster because the tool knows the system better. And you can see such scripting runs with multiple cases. It's maybe a little bit easier for if you're doing this at lunchtime or it's evening, depending on the complexity. Okay, then we will switch over to the output. We open it, and the output is a copy of the input. And there is tool wrote the results of the torque and the transmission error here in the Excel sheet. And you can see here it's the mesh design A. It's unmodified, it's a straight line going upstairs. This is a typical straight line for unmodified gears. And you can see the transmission error with this crowning effects for design B. Now, if you're doing a very smarter scripting, and the scripting is also, by side, I forgot to explain, the scripting is a JavaScript. It's very simple to use, I think so. It's easy to learn by yourself. And with the scriptings, you can specify loops and specify that all the tolerances are in combinations will run one after the other. And at the end, you can do post-processing like this one, that you will write here your specification of the modifications and then the results, one line after below the other. And then you can get something like this one, a parameter study of a multiple run of all tolerance combinations. You can do something here, the Hull curve of the max values, the min values, the median, mean. You can see if you run all the tolerances, you will always get such a band of possible transmission errors, not only one line for the base design, but a corridor, tolerance corridor for all possible designs. Now we just switch back to the presentation. Then last but not least, I like to show shortly the eigenfrequencies and eigenvalue analysis in the FVA Workbench. To get the eigenfrequencies, the transmission system with all components has to be transferred into a vibration model with methods, springs, and damper. But in the FVA Workbench, we have no dynamic solver, so we are not performing full dynamic analysis. For this, we can export our transmission model in a standardized REXS data format and use the multiple body simulation tool SynPack. This is supporting at the moment the REXS data interface standard. In the future, the tool AVL Excite, but there the implementation of the REXS interface is still going on. If you want to know more about REXS standard, you can visit the website www.rexs.info. To get the eigenfrequencies, we only need the methods, the stiffnesses of the vibration model, no dumping and so on. There are unlimited eigenfrequencies depending on the masses you have specified and the frequency and the speeds you're running. There's a lot of unlimited possible, but only a low number is technically relevant. These which occur at operating speeds and where the gears are moving against each other. This is phase or in phase or out of phase or the moving of this gear mesh. We can derive lateral, torsional, and mixed eigenmodes. auxiliary swing modes. These animations you can directly get from the FVA Workbench. As a result of the eigenvalue analysis, we get a Campbell diagram. In the horizontal direction, the eigenfrequencies are shown, besides the eigenmode and eigenfrequency, with corresponding shaft are described. The red lines are the gear meshing orders, the gray stripes are showing the operating speeds of the shafts, and the critical points are highlighted where gear meshing order, shaft speed, eigenfrequency, and eigenmode can interact and lead to resonances. Such simulated Campbell diagrams can and should be, the best would be, validated and compared with measured Campbell diagrams. Typically, the eigenfrequency analysis should be performed regular at the beginning of the gearbox design process to avoid the risk of resonance directly at the base design. At the end, it's often not so easy to change this complex design, but I will show you a simple example now where it's not so complicated. Otherwise, if you're doing this analysis at the end, you have to change the number of teeth for the meshing order, or the distance of the bearings for the stiffness, and so on. And this is a little bit difficult at the end of your design process. So this should be done starting at the beginning of your design. Now we came to our last example for today. There I will switch over to the FVA Workbench again. Which one? 6.1. You can see the 6.1. Here I will choose again one of our example models, our easy entry models. I decided for the FVA virtual gear unit. This will take a couple of seconds. There's also FE mesh included. And now you can see only this, again, this housing is closed. Let me open it shortly, right click, cutting plane for FM components. Oh, this is a wrong direction. So we switch the cutting direction. And we switch to local cutting plane. Here you can see it's an industrial gearbox again. Three gear stages. You have one bevel stage here, and you have two cylindrical stages, one with a helical gear and one with a spur gear. To analyze now the eigenvalue analysis, you have to select the casing first and deselect the FEM stiffness, because this is not supported for this eigenvalue analysis. It's also here mentioned. Then we go again to the gear unit, the calculation targets, deselect all calculations which are predefined in this model. Then we are going to dynamics calculate eigenvalues and eigenmodes. Activate this button here. And then it's enough and we can run this model. I think this was very fast, should be not take a lot of time. You can see here now the result. For gear excitations, it's not gear excitation, I need another report for the eigenfrequencies. I think this is included in the system report, but I have also defined a customized user-defined report template only with two outputs that I can show it easier to you. Then I can open this report, and you can see here the two stages and the bevel stage, the cylindrical or bevel. And you can see here it's a Campbell diagram with shaft 1 and shaft 2. And here you can see there's one critical point. This is at an eigenfrequency of 614 Hertz. This is a pure torsional eigenmode, and Campbell's meshing order is 2. You can see it's close to the border of this operating speed of the shaft 6. So if I will now increase the eigenfrequency, therefore I have to increase the torsional stiffness a little bit, and then I will shift the eigenfrequency upwards and the intersection point with a second order out of this operating speed, somewhere in this direction. And then the point will leave. The other meshes, you can see here the cylindrical stage. The other one, it says uncritical. For the bevel stage, you can see again here, it's also a critical one, also the same eigenfrequency, the torsional one, which can lead to troubles or not, depending on your design. This is a critical point, which may lead to resonances. And now our challenge is to increase the torsional stiffness, to increase the eigenfrequency. Going back to our wrong song, 6.1, this one. So I will make a cut here for a better view. This is our design, our system. One moment, I will. And how to increase the torsional stiffness. You can see here it's a thick one. I don't like to change the bearing seats and don't like to change the input and output diameters. This is the interface to the outside. I don't like, this is a very thick part here. I cannot change a lot because there's a pinion on the shaft. But this is a very thin and long shaft. I think here you can increase torsional stiffness a little bit. And I will do this at this diameter here. This here, I think I can increase a little bit, and then the torsional stiffness will increase too. In the shaft contour, you can see I have selected here, and this editor is opened. It is the biggest diameter, the 108. I will increase it slightly with 120. And now the stiffness should be better for the torsion. Run the calculation again. Then I will set this as reference. The next one, compare with the reference. And now we got both results. So here you can see this critical point as 614 Hertz. And here the critical point left is solved. Why it is gone, this critical point? Because I changed the rotational stiffness, and now we have an eigenfrequency increased from 614 up to 657, and we are out of the operating speed of the shaft. To check if I damaged everything else. No, the second one's fine, still fine. And the bevel stage, it is the same. Here I shifted out of the operating speed of the shaft. Now I go back to the presentation. Now I will finish this web seminar with a short summary. Today I gave a short introduction about gear excitations and micro-modifications as toolbox for design improvements. Then we have seen the operating and the usage of the FVA-Workbench with respect on gear excitations in the live demo. Next step was a short sneak on scripting, also with a live demo. And at the end, we have seen the eigenfrequencies and eigenvalues analysis in the FVA-Workbench. Now I'd like to finish this presentation. I hope you got interesting information out of this web seminar, and thanks a lot for your participation. If you like to stay informed on our services, you can follow us at Twitter, LinkedIn, or you can subscribe our newsletter. And now I'm ready to answer your questions. If you have later on questions and want to talk about this topic, do not hesitate to contact me via the contact formula on our website in the section Company and Contact Us. And now I will be looking at your questions. One moment, please. There's one question if the RexS import is also using with FVA Virtual Dynamics. Not yet. I don't know if this is planned, but this can you find on the RexS info site on the web. I think for multidynamics and multi-body analysis at the moment, the only company which have implemented the RexS interface is Simpac, and I know that FVA Excite is following soon. Some questions else? Yeah, it's okay. This was I was too late. What is the programming language used for scripting in the FVA Workbench? This language is JavaScript. Something else you want to know? If I will share this presentation? No, I will not share the presentation directly, but in a few days, a record of this web seminar will be online on our website and on YouTube. I cannot see any more questions. No, nothing else. Ah, it's here. Is the housing stiffness for the lead modification considered? Yes, it is. Of course, it is. Yes, it is the most important, one of the most important. The housing stiffness I have only deactivated for the eigenvalue, eigenfrequency analysis. Otherwise, the housing stiffness is essential for the stiffness of your complex system, especially for this example, for the industrial gearbox. There are very high torques and you get deformations of your system under load. Yes, this housing stiffness has a great effect on your gear mesh misalignment. The script, again, the script which was shown, was it in the VBA? No, this was JavaScript. Another question. What is for critical intersection on Campbell diagram? We decided if you have intersection lines, it's not deciding the excitation itself. It's just the Campbell diagram. The critical point is specified if you have an intersection of your operating speed, of your eigenfrequency of parts, your shafts and gears and so on, your meshing order, and if the eigenmode is if the gears are moving against each other, in phase or out of phase. And this is our criteria if this can be an issue. If you have a perfect meshing gear, great design, then there has not to be an issue. There may be an issue, but it's not. It's just to avoid that there could be resonances. I cannot see more questions. Then, again, if you have later on questions or want to discuss with me or want to have other questions and so on, do not hesitate to contact me via the contact formula, or if you are a customer, you can also write on our ticket system and do a question. Oh, Yeah. Oh, another question. Do our company offer thesis positions in exactly these fields? At the moment, we have no student activities in our company. This is depending on I think about this. If we have some topics, you can handle it with students for a thesis, and I think about this. What is the difference in line load and max pressure? The area. It's a line load. It's not the line load per area is the pressure. If you will see the pressure distribution, it's similar but not exactly the same. You have line load is Newton per millimeter, and pressure is Newton per square millimeter or megapascal. I think for the daily business, if you're using a line load or pressure, it's for the gear contact itself, it's doesn't care. But for the stresses are mostly better than line loads. But for the load distribution, the line loads are fine. Okay, I think we should finish this for today. Then thanks again for your participation. Then I wish you goodbye and stay healthy.